All right, so this is a new chapter. Um, the motivation I want to give you about what we're about to learn is we're gonna learn how to find area under a curve in this chapter. And what do we mean by area under a curve? Like, for example, if you talk about area under a line, that's easy, right? Because lines, you can break them into rectangles, into triangles. There are formulas for them. They're relatively easy to work with. Curves, if you have a circle, we know the area under a circle, of course. But what if what you have is simply a function, f of x equals, let's say, x cubed minus x squared, just any function f of x. Then the question is, how would you find the area under this curve? Like in Calc 2, for example, you're going to rotate that curve around the x-axis, and you're going to find the volume of the solid generated. But this is not a typical object. We don't have a formula for the volume of this. It's not a cylinder. It's not a cone. It's not a sphere. So what do you do, in other words, if you have unusual objects like that? And again, same idea we'll be using Calc 2 when you're doing volume. How do you find the area under a given function where there's no formula for it? That's where we're going to be headed today. And we'll actually be able to answer that question for some simple functions today. And we'll generalize it even more next time. OK, to get to that end, we need to know a few things about the summation notation. So let's begin with that. All right, so our main topic is approximating area. And to understand that, we need to know what is called a Riemann sum. But we're going to begin with some basic summation expressions. Now, how many of you have seen that notation sigma before in perhaps pre-calculus or statistics, right? This notation represents sum in mathematics, right? And if I put an index on the bottom, say I from 1 to n, that means you're going to add up the first n elements of that sequence a sub I. Like in this case, summation of a sub I from 1 to n. That's a compact notation. And what that means is an expanded form. It's a sub 1 plus a sub 2 all the way to a sub n. Now, it depends on what a sub I is as to what you're going to be expanding. This is your generic term of your sequence. So for example, if it's just I, how would you expand this example in number 1? So let's start with the lower index when I equals 1, right? So you're plugging 1 into I, that's 1, right? Summation means keep adding these. Then the next term would be what? Just a 2, and we're going to go like this until we add up the first 10 terms. The last term is going to be I equals 10. OK, what about the next one? Of course, you could get an answer for this. But right now, I just want you to be more familiar with how do you expand a summation. How do you do the summation I squared from 1 to 5? So starting with 1, we're plugging 1 into I squared. So that will be 1 squared, right? Plugging now 2. So you keep incrementing it 1 at a time. When I is 2, you have 2 squared, right? So this turns out to be the sum of the first 5 squares then. Would everyone agree with that? So because we stopped and the upper limit was 5. OK, what will it be for the next one? And again, we can get a number for this easily. The next one, summation I from 1 to 5 was just the number 4. There is no I inside the summation. Any thoughts how we could expand that one? This is like the sum of a constant. For example, when I is 1, we have a 4, right? When I is 2, we still have a 4, right? When I is 3, we still have a 4. It's just a constant, doesn't depend on I. It's always the same thing. So basically, we're adding 5 4s, right? How do I know it's 5? Because the upper limit was 5. So in general, if you're adding a constant, can you give me a shortcut rule as what the answer is going to be? Just multiply the upper limit by that constant. If there's no I inside the summation, then all you're going to have is 5 times 4 in this case, or 20. You just multiply that constant by the upper limit. Oops. 5 times 4, or 20. In a little bit, we're going to summarize some of these results in more general terms. OK, what about something like this? Summation I from 1 to 3 of 2I plus 1. How could we expand that one out? What would be my first term? So I start by plugging in I equals 1. So that's like 2 times 1 plus 1, right? OK, then What happens if I is 2? Two times 2 plus 1. So basically, we're just replacing the I. We're leaving everything else the same. And should I go a few more terms? One more, right? Because the upper limit is 3. So it will be 2 times 3. 2 times 3 plus 1. Now, let me ask you a question. Could I have written this as follows? 2 times 1 plus 2 times 2 plus 2 times 3, and then 1 plus 1 plus 1. Could I have written it like that? This is like the associative property of addition, right? You can add any two terms first and then add the other ones later, right? So what I did was I took this one, and this one. I wrote them first, and then the 1 plus 1 plus 1, I wrote them last. We can do that, right, with summation, because, again, you can add the first two first or the last two first. It doesn't matter in the end. So could I have written it like this then? Is this the same thing as summation of 2I plus summation of 1 as I goes from 1 to 3? Could I do this? I'm going to put a question mark because we're discussing it right now. We're not sure yet. Look at the original question. It was summation of 2I plus 1, right? And at the end, I broke it down as summation of 2I plus summation of 1. Can we do this based on this one example? Well, if we expanded it out, we collected the 2 times 1, 2 times 2, 2 times 3 together, right? That's my 2 times I, as I goes from 1 to 3. And then the 1 plus 1 plus 1, that's my summation of 1 as I goes from 1 to 3. So does it look like we can do this? So in general, then, we can break up a summation. If you have summation of A plus B, you can see this is the summation of A plus the summation of B. And actually, this next properties of sigma are going to basically help us realize these concepts or just reiterate them. So here are the 3 properties of sigma. Number 1, if you're just adding a constant as I goes from 1 to n of C, we just talked about that one, right? If you're just adding a constant, it's as if you're multiplying C n times by itself, right? Because it's C plus C plus C, n of them, so that's n times C. Property number 2 is also something we looked at right now. If you have summation of A sub I plus B sub I or A sub I minus B sub I, you can write that as 2 separate sum. Summation of A sub I plus or minus summation of B sub I, just like we've seen up there. You can split a summation. And the third property it tells us what to do for a constant multiple. If you have a constant C times A sub I, the third property is telling us you can factor the C outside of the summation sign. You see, we took the C out. And why is C a constant and A sub I is not a constant? What's the difference between them? In other words, how do I know if something is a constant or something is a variable? So that I will know the constants can be taken out, but the other stuff cannot be taken out. How do I know when something is a constant? It should not have an I in it, okay? Because this index is running through I is going from 1 to n, right? So anything that has an I in it will be considered to be a variable. Whereas if C is just a number, it doesn't depend on I. In that case, it's just a constant. It can be factored outside. Now, let me show you a very quick example of this one. Let's say that we have summation of 3 times I squared as I goes from 1 to 5. How would you expand that? It's 3 times 1 square, right? Plus 3 times 2 square, correct? All the way to 3 times 5 square. Could I take out the 3's from each of these terms? We certainly can. So take the 3 out, so 1 square all the way to 5 square. So as a summation, could I write it like this then? 3, take the 3 out from this sum. 3 times summation of I square as I goes from 1 to 5. Could I write it like that? Certainly, right? It's really a simple property of addition that you can factor it out. If every term has the same factor, you can take it outside. Basically, that's what this rule number 3 is telling us that we can do. Okay. Now, these were called properties of sigma. Now, I'm going to show you 3 rules. These are called some formulas, summation formulas. Now, the ones that we've just learned, these are very important. You guys need to know these. The next three, you don't have to memorize them. I would give them to you if there need be. And we're going to use them quite a lot today. But these are some formulas, some shortcut rules, like how can you find the summation of the first I terms? How can you find this, rather I should say, the summation of the first n whole numbers? Second one tells you, how do you find the summation of the first whole number squares? And the other one is, how do you find the first n whole number cubes? So these three formulas will tell us how we can quickly find those. I'm going to try to show you a quick proof for the first one. And just know that if you want to prove the other ones, you could use something called induction. It's a very commonly used method to prove things like this. Like you assume it's true for n, and you try to prove it for n plus 1. Some of you may have seen it in pre-calculus. So I'm just going to prove the first one. Summation of I as I goes from 1 to n is n times n plus 1 over 2. And here's how we can prove it. And to make it a little bit easier on us, let me pick some numbers just to show you the idea. Let's say we're going to add up from 1 to 100. Okay, so say that we want to find out 1 plus 2 plus 3 all the way to, let's say, 100. And it's actually said that it was Gauss, a very, very famous mathematician, who came out with this proof in the first place. And the rumor goes that he was in elementary school or something. I mean, this was just a mathematical genius. And again, the rumor goes that, the teacher gave them this job, add the first 100 numbers, thinking that it's going to take the students a very long time. Of course, Gauss, in a few seconds, comes up with the answer. And it's said that this is how he solved it. He wrote them backwards second time. So 100 plus 99 plus 98, all the way down to 1, right? And he added each of the columns, like what is 100 plus 101? 1 plus 100. That's 101, right? What's 99 plus 2? 101. What is 3 plus 98? Every one of these sums is going to be 101, right? But now how many 101s do we have? Because how many columns do we have? We have 100 columns. So we have, right now, we have 100 101s, right? We have 100 101s, except that we did it twice. We added the numbers going up and going down. So to compensate for that, what should I do to this now? I should divide it by 2, right? Because I've basically added 1 through 100 and also backwards, 100 through 1. Basically, I've added that sum twice. So he divides this by 2 to come up with just one sum, 1 through 100. So this would be his answer right there. But instead of 100, what if he had n? So his answer would be 100. Instead of 100, if you have an n, it will be n times what? n plus 1 divided by 2. And if you look over here, that's exactly what formula we had stated, right? N times n plus 1 over 2. And just out of curiosity, then, what is the sum of the first 100 terms then? If you're going to apply this formula, what is 100 times 101 over 2? So 100 over 2 is 50, right? So basically, you need to multiply 50 times 101. And what is it, like 5,050? Is that right? OK. So again, it can be done in a matter of seconds if you can think of this interesting way. Now, the other ones, number 2 and 3, are not so easy to prove. They are more complicated, and one really needs to use induction, or there are some other ways to do it also, but I think induction is one of the most direct ways to prove 2 or 3. And if you're wondering, how are they even coming up with something like this? How did they come up with these formulas in the first place? One year I had an honor student. He actually came up with these himself. He did a little table. He put like I, let's say 1, 2, 3. And then like for I squared, he wrote down the first few squares. So for example, the first one would be 1 squared is 1, 2 squared is 4, 3 squared is 9. And then he tried to find a polynomial, basically, that would go through these points. And basically, if you try to do a regression and try to see what polynomial would fit there, it turns out that this is the polynomial that best fits those points. And then you can do something similar. Use 4 points for the I cube, and you can get that one as well. All right. So some more examples now based on what we just learned, all the properties we just learned. Let's simplify the following. So for example, summation of I as I goes from 1 to 60. So here we're going to use the formula, the Gauss formula, right? Gauss's formula, n times n plus 1 over 2. What is our n here? Our n is 60. So the formula says take 60 times 61 divided by 2. And let me know what you're getting there. So we don't have to write 1 plus 2 plus all the way to 60. That's very long. With the shortcut method, the answer is 1830. And can somebody verify, please? Okay. What about the next one? Summation of I squared from 1 through 20. And again, the extended form is like 1 squared plus 2 squared all the way to 20 squared. But if you apply the formula was once again n times n plus 1 times 2n plus 1 all over 6. Now this formula you don't have to memorize. Although the very first one is so basic, I would recommend you to try to remember that one. That's going to come up in a lot of different places. But the summation I squared and I cubed for sure, I would provide those for you. So summation of I squared, in this case, the upper limit is 20. So just plug in 20 for n, right? So we'll have 20 times 21 times. So now you want 2 times 20 plus 1, or 41 divided by 6. And what you guys get for that? Okay, would everyone agree? Okay, great. And what about summation of I cubed? Interestingly enough, the formula was the original formula, the n times n plus 1 over 2, but to the second power. So if your n is 15, it's going to be 15 times 16 over 2 altogether squared. And let's see what that is. Basically, 2 goes into 16 8 times, so you could just do 15 times 8 and then square that. And did you guys get 14,400? Okay. How about the next one? Summation of 3 as I goes from 1 to 30. We're adding just a constant here, right? So what was the simple rule for that? Just multiply, exactly. 3 times 30, that will be 90. Okay, the next one is a little bit different. If I can erase what I have there. Okay. Yeah, I can see several ways to do this, but I think the easiest one, we don't have a formula that applies directly to 3k minus 1 squared. We have a formula that applies to just k squared or I squared, right? So our best bet right now is to expand that binomial. Okay, so let's rewrite the binomial in expanded form. That's our first step, because we don't have a formula just for this expression squared. So the first one squared is what? So I'm squaring the binomial. What is the first quantity squared? 9k squared. By the way, I've been using the index I, but as you can see, you can use k. Sometimes they use j or any letter, just like the function f of x. It could be done in any variable. A summation could be run over any variable as well. Okay, the middle term, minus 2 times the first and the second, right? So that's minus 6k. And the last one, the square of the last term, which is 1, right? Now I have a sigma of a plus or minus expression, a sigma of like a sub I plus or minus b sub I type of expression. How can I rewrite this? Separately, right? One of the rules that we just learned was if you have a summation of a sub I plus or minus b sub I, you can distribute your summation over it. And while you're distributing it, if there are any constants, you can also factor those out, right? So for example, summation of 9k squared, the 9 is a constant, right? So I can take out the 9 there. So this can be written as 9 times summation of k squared. In each case, k goes from 1 to 15. I'll put that in a minute. The next one, distribute the summation sign and take out the constant. Then I take out the 6, so you have summation of k. As k goes from 1 to 15. And the last one, just summation of 1 In each case, k is going from 1 to 15. Okay. Now, do we know how to handle each one of these by certain formulas? Like this first one, sum of the first 15 squares. There is a formula for that, right? Summation of the first 15 whole numbers, we have a formula for that. And the last one is just a constant. So let me have you guys finish this question and let me know, please, what you're getting. So the rule for k squared was n times n plus 1 plus 2n plus 1 over 6. The rule for summation of k was n times n plus 1 over 2. And the last one, just a constant multiplied by the upper limit, 15 times 1. And some of you maybe already did this. What was your answer? Daryl, could you say it again, please? 455. Thank you. And everybody agrees with that? Okay, so now we know how to expand something, distribute the sigma using all the properties we've used basically in this last example. So you can simplify even more complicated sums if you can break them down into smaller components. Okay, any questions so far about the sigma notation? Okay.